theorem, one more result about this set of all linear transformations between two vector spaces. So let's make it in a kind of a theorem. The theorem is, let V and W be two vector spaces. Vector spaces are also known as linear spaces. So maybe you will find somewhere written a linear space term. So it is actually a vector space over the same field F. Over a same field F, and let dimension of V is equal to n, and dimension of W is equal to m. Then, since we know that LVW is a vector space also, so we can define it as dimension. Then dimension of the linear space LVW, this is equal to m into n, where we actually already know that what is this LVW. So let's also write it here for the sake of completeness, where this LVW is the set of all linear transformations from V to W. So we know that LVW is a vector space. Now here V has dimension equal to n, and W has dimension equal to m. Then the dimension of the set of all linear transformations from V into W is the product of the dimensions of these individual vector spaces. So now let us do the proof. The proof is not actually difficult. Now what we have to prove? We just have to prove that the dimension of LVW is equal to m into n. And you proving that the dimension is equal to m into n, it means that we actually need to find a linearly independent subset from the set of all linear transformations from V into W. Then the cardinality of that linearly independent set must be equal to mn, and it should span the whole LVW. And once we can find such a linearly independent subset whose cardinality is equal to m into n and spans the whole LVW, it means that linearly independent subset would form the basis of this LVW. And we know that the cardinality of the basis is defined to be the dimension of this vector space. So therefore, we actually need to find out that there is a basis that contains m into n number of terms, and our proof is complete. So now let's define those linear transformations in this LVW, and then form a set of those linear transformations which are mn in number, then prove that it is linearly independent and spans L of VW, and our proof will be done that dimension of LVW is equal to m into n. So did you get the idea what we have to do?
Yes, sir.
चलो ठीक है, आप बता सकते हो हमें करना क्या है, अब उसके बाद हम करेंगे, लेकिन हमें आइडिया क्या है, हमें क्या करना है? So the idea is we just have to form a linearly independent subset of LVW. इसमें हमें एक linearly independent subset choose करना होगा, और हम फिर दिखाएंगे कि वो subset linearly, we actually first have to choose a subset, फिर हम दिखाएंगे वो subset independent है, and then it spans LVW, and its cardinality is equal to m into n, and that actually makes that subset into a basis of LVW, and then the number of elements in that basis will be equal to the dimension of this vector space. लेकिन जब हम उसमें पहले ही लेंगे m into n number of elements, that means the dimension of LVW will be equal to m into n. Keeping in mind that whenever we construct any basis of a vector space, then any basis will contain the same number of elements. ये आप जानते होंगे, ठीक है? Okay, so first we will choose a basis of V, and then we will choose a basis of W. So let this V1, V2, so on, Vn, and W1, W2, and Wm be the basis of V and W respectively. So once we have chosen the two bases, now let's recall a result here. हमने एक theorem की थी जो हमने शायद पहले ही दिन की थी. The theorem was like this. If V1 to suppose some Vk is a basis of V, and W1 to Wk is any set of vectors, is any subset of W, then there exists a unique linear transformation T from V into W such that
T of Pi is equal to
T of Pi is equal to WY. ठीक है? तो अब यहाँ पे वो K और K कॉमन होना जरूरी नहीं है. We can change this K. Just the idea is, अगर हमारे पास basis होगी, then for any subset of W, we can always define a unique linear transformation which maps this Vi into Wi. तो इस theorem का अब हम यहाँ पे use करेंगे, because here we also have a basis of V, and then we also have a subset of W. तो यहाँ पे basis जो हम choose कर रहे हैं, that is V1, V2, Vn, और जो फिर वहाँ पे वो subset हम choose करेंगे, that will be W1, W2, Wn. तो इन दो sets पे अब हम use करेंगे वो theorem, then we can define a linear transformation from V into W such that T of Vi is equal to some Wj here. So then there is a unique linear transformation then there is a unique linear transformation T from V into W such that T of Vi is equal to Wg, where 1 is less or equal to I, less or equal to n, and 1 is less or equal to G is less or equal to m. तो इस तरह की linear transformation हम हमेशा define कर सकते हैं, and this kind of a linear transformation is always unique. Now we will try to define the elements in this L of VW which will form the basis. Now define a mapping. Not actually a mapping, we will precisely call it a linear transformation. Now define a linear transformation T Ji from V into W. So Ji हमने इसलिए mention किया because now then this J will vary over this vector, vary over the basis of W, and this I will vary over the indices of the basis of V, so that we will get mn number of transformations. So then Tji from V into W by Tji of Vi is equal to Wg. तो जो यहाँ पे हमने स्टेटमेंट लिखा, ये स्टेटमेंट हमने जस्ट लिखा to recall that theorem that there is a unique linear transformation from V into W which satisfies T of Pi is equal to Wj for some fixed I and this fixed J. तो इसी तरह से अब हम linear transformation इस आइडिया को यूज करके डिफाइन कर सकते हैं and name that linear transformation as Tji from V into W, and we will define it by Tji of Vi is equal to Wj, and Tji of Vk is equal to 0 for all I not equal to k. We have to clearly look how we have defined this linear transformation. यहाँ पे अगर ये I और I index same होगा, then the image of Vi is equal to defined by Wj और ये j यहाँ पे same है. But if this I and this Vi, जो यहाँ पे index of V होगा, if these indices happen to be different, when I is not equal to k, then we define Tji of Vk is equal to 0 for that Vk. So Tji maps Vi into Wj and it maps every other Vi into 0. ठीक है? So this is how we have defined this linear transformation. Now construct a set B. Now consider a set B that contains the linear transformations Tji such that one is less or equal to I, less or equal to n, one is less or equal to j, less or equal to m. So then, what is cardinality of B m into n? ठीक है यहाँ तक? आपको आवाज आ रही है मेरी?
यस सर, यस सर।
तो यहाँ तक आपको
Yes, sir.
हमने कैसे किया? अभी हमने कुछ नहीं किया, अब हमें दिखाना है जो हमें दिखाना है, ठीक है? तो अभी तक हमने लीनियर ट्रांसफॉर्मेशंस डिफाइन की एंड देन वी कंस्ट्रक्टेड दिस सेट. Its order is equal to mn, but now our task starts. We have to show that this set spans the whole LVW and this set is also linearly independent. तो ये दो steps अगर हमने prove किए, then we are done with showing that this B actually forms a basis. And so, because its order is equal to mn, its dimension of LVW becomes equal to mn. Now we show B spans LVW. ठीक है? तो इसको स्पेन दिखाने के लिए B spans LVW, it means that every vector, every linear transformation inside LVW can be written as a linear combination of the vectors from B. So that means every linear transformation, whenever we can define a linear transformation from V into W, that can be written as a linear combination of the linear transformation Tji, where I runs between this range and J has this range. So let's choose, let T belongs to LVW. तो अब हम दिखाएंगे this T can be written as a linear combination of these Tji's. Then, now since Vi belongs to V and T from and T maps V into W. Thus, where is it T of Vi? It belongs to W. यहाँ तक ठीक है?
यस सर।
Okay, so once we have chosen an element of W, now we know what is the basis of W. So using that basis, we can express this T of Vi as a linear combination of the vectors from the basis. But this W1, W2, so on, Wm is a basis of W. Thus, T of Vi, this can be written as a linear combination, summation j from 1 to m, alpha ji wg.
W.
ठीक है? Now this index I is fixed, तो यहाँ पे से confuse नहीं होना. This is just to mention, actually just to have its role. with vi also. तो इसलिए हमने लिखा alpha ji. Otherwise, we could just have written alpha j, where this alpha 1i, this just a name, alpha 2i, and so on, alpha mi. They are the elements of F. ठीक है? So now using the definition of now using the definition of TGI, we have, तो हमने किस तरह से इसको डिफाइन किया था? We have defined TGI of PI is equal to WG and TGI of VK is equal to 0 for all K not equal to I. इस तरह से हमने मैपिंग TGI डिफाइन की थी. So thus, तो अब यहाँ पे हम अब अगले पेज पे हम लिखते हैं ये. So thus we have thus
Sir, एक मिनट please previous page.
previous page.
आप ये लिखते हो या स्क्रीनशॉट लेते हो?
सर हम लिखते हैं.
बहुत अच्छी बात है.
स्क्रीनशॉट सर।
मैं फास्ट तो नहीं लिख रहा हूँ.
Yes, sir.
अभी भी फास्ट लिख रहा हूँ.
तो सर पेज फिर जल्दी ये करते थे.
चलो वो मसला नहीं है, तो वो तो फिर वापस भी हम आ सकते हैं. चलो आप लिख लिया ये.
जी सर हो गया.
Yes, sir.
जी सर.
Thus T of Vi is equal to, let's again repeat it, this is equal to summation j from 1 to m alpha ji wg. Now this is equal. Now let's look back here. अब यहाँ पे ये मैंने फिर से वही लिख दिया, लेकिन यहाँ पे जो wj है इसकी जगह पे हम लिख सकते हैं this tji of vi. So this is equal to this is equal to summation j from 1 to n m alpha ji. Now wj is equal to tji of tji of vi. ठीक है? Now let's expand it for a while. Now here j varies, so it is alpha 1i t 1i vi. This is the first term. Then the second term is alpha 2i t 2i vi. इसी तरह से then so on alpha mi t mi. यहाँ तक ठीक है? हमने just expand इसको किया by using the different values of j and where j varies from 1 to m. Now let's look at, अब मैं यहाँ पे कुछ steps लिखूंगा, एक line लिखूंगा, then we will see मैंने वो line किस तरह से लिखी. So the first thing is we will write alpha 1 1. I will vary I. ये I मैं vary करूंगा, लेकिन vi मैं यहीं पे रखूंगा क्योंकि यहाँ पे हमें vi हर जगह पे है और लेफ्ट हैंड साइड में हम इमेज यहाँ पे असल में कैलकुलेट कर रहे हैं t of vi. So this is t of 1 1 vi अपनी ही जगह पे. Then alpha of 1 2 t of 1 2 vi. Then so on. तो इसी तरह से बीच में एक टर्म ये भी आ जाएगी alpha 1i t of 1i vi. Then so on alpha 1 n t of 1n vi. Now forget about this statement, this expansion. अब इसकी तरफ हम देखेंगे. What about t11 of vi? ये किसके बराबर है?
W.
सर लास्ट टर्म में तो m है ना.
0.
0 के बराबर है ना ये पहली
0
टर्म.
के लिए
हमने कैसी मैपिंग डिफाइन की थी? t of tji of vi.
VK.
Sorry, tj of vk is equal to
Equal
0
to
for
0.
all I not equal to,
I
वही
not
चीज हमने यहाँ पे भी किया। तो ये टर्म हमने अपनी जगह पे लिखी जो यहाँ पे पहली टर्म थी। अब हमने इसमें ऐड किए कुछ टर्म्स t11 ऑफ वी, लेकिन ये 0 के बराबर है। t12 ऑफ वी ये भी 0 है, ये खुद ही यही टर्म है, और बाकी सब टर्म्स इसमें 0 है। तो असल में हमने इस पहली टर्म की जगह पे इतनी सारी टर्म्स लिख दी। तो ये भी हमने क्यों किया ये हमें अभी पता चल जाएगा। देन द नेक्स्ट इज, इसी तरह से सेकंड के लिए भी हम यही करेंगे। सो सेकंड विल बी अल्फा 21 t21 vi, then alpha 22 t22 vi, then so on, alpha 2i t2i, then vi, then so on, alpha to n, because I is varying from 1 to n, तो इसीलिए हम n तक लिखते हैं इसको 1n vi, and similarly then plus so on, and now the last one alpha m1, आपको आवाज तो नहीं आ रही है फोन की? चलिए अभी बंद हो जाएगा खुद ही। then t m1 vi, then alpha m2 tm2 vi, then so on, alpha mi,
Mn.
एक जगह पे ये भी होगा, पहले हम ये भी लिखेंगे ना, then t mi vi, then the last term is so on t, this is alpha, इसमें क्यों स्पेस
Mn.
हो गई, then so on, then plus alpha mn tmn vi। ये स्टेप बिल्कुल इजी था, हमें सिर्फ इन बाकी इसमें टर्म सारी ऐड करनी है, और ये जो पूरा सेट आ जाएगा, दिस एक्टिवली इक्वल टू दिस सम। बट नाउ वी कैन राइट इट इन अ कॉम्पैक्ट फॉर्म लाइक दिस। नाउ दिस कैन बी रिटन एज समेशन। तो इस सिर्फ इस समेशन को लिखने के लिए मैंने इसको एक्सपेंड किया, दिस समेशन j फ्रॉम 1 to m, देन वी कैन राइट summation I from 1 to n alpha ji tji of vi। तो इस समेशन में अब कितनी टर्म्स है, दिस m into n number of terms। तो यहाँ पे भी I runs from 1 to n, j runs from 1 to m, so therefore this sum contains all of these terms। लेकिन ये सारी टर्म सिर्फ इस सम के बराबर है, and that's equal to t of vi। So that means actually we have expressed this t of vi as a linear combination of tji's। ठीक है यहाँ तक अब? So that is what we have done। We have shown that t of vi belongs to the span of B। ये दिखाया ना हमने, हमने ti चूज किया था w में से, और अब हमने t of vi, हमने t चूज किया था l of vw में से। तो अब हमने t, इसकी जो any linear transformation होगी, it's actually the image of the linear combination of tji's। तो यहाँ पे vi और vi को अगर यहाँ पे नहीं रखेंगे, then t is equal to the linear combination of these things। ठीक है? So therefore every linear transformation t in LVW can be expressed as a linear combination of tji's। So is it clear now?
Sir.
हाँ बताइए। हाँ समझ में आया आपको?
Yes, sir.
Okay, so we are done with one step. Then the next step is to show that this set is linearly independent. Now to show Now we show B is linearly independent. तो B को लीनियरली इंडिपेंडेंट दिखाने के लिए हम हमें डेफिनेशन डायरेक्टली हम यूज करेंगे. We will choose a set. We will choose this B and then consider a linear combination over the scalars from F and then show that every coefficient is equal to 0. So suppose summation J from 1 to M summation I from 1 to N. Let us write beta now. Beta Ji Tji is equal to 0. Suppose this is equal to 0. So once we have this equal to 0, that is thus this equal to 0 transformation. तो अब हमें प्रूव करना होगा this beta Ji is equal to 0 for every J and for every I. So thus summation J from 1 to M summation I from 1 to N beta Ji Tji of any Vi. तो हम यहाँ पे अगर हम कुछ लिखते तो यहाँ पे हम लिखेंगे VK. ठीक है. This is for any VK. So in order to be more general.
पहले बे करो सर हम पहले बे करो हम स्क्रीनशॉट लेंगे.
तो मैं इतना स्लो लिखता हूँ तो आपको ये साथ साथ लिखना चाहिए. Okay, now okay, or this is summation. ये लीनियर इंडिपेंडेंस मुश्किल नहीं है, वो थोड़ा सा लंबा था लेकिन ये अब वैसा नहीं है. This summation I from 1 to N then beta Ji. Now look at this Tji of Pk. This will be equal to 0 if I is not equal to K and this will be equal to Wj if I is equal to K. ठीक है. तो यहाँ पे सिर्फ एक ही टर्म बच जाएगी, that is Wj, and so this is equal to, ये स्टेप आपको आया समझ? Because Tji of Vk, this is equal to Wj if I is equal to J and this is equal to 0 if I is equal to K, if I is not equal to K. इसी तरह से हमने डिफाइन की थी ना मैपिंग TJI. अगर I K के बराबर होगा then this mapping is equal to Wj. लेकिन अगर I K के बराबर नहीं होगा then this is equal to 0. तो जब हम यहाँ पे एक्सपेंड करेंगे तो जो यहाँ पे इमेजेस बन जाएंगी Tj1 of Vk, Tj2 of Vk and so on. तो Tjk of Vk that will be equal to Wk. हमें यहाँ पे Wk लिखना है. तो चलो इसको Wk लिखते हैं. J में भी कोई मसला नहीं था. So let's write K here. So this is K here. तो जब I K के बराबर होगा then this is equal to, तो लेकिन ये यहाँ ना हमने पहले ही ठीक लिखा था, because this depends on this J. So this is equal to Wg. ठीक है. समझ आया आपको यहाँ तक? सिर्फ यही एक इंपॉर्टेंट स्टेप है इसमें, और कुछ नहीं है इस प्रूफ में. आपको आवाज आ रही है मेरी?
जी सर.
समझ में आया यहाँ पे?
हाँ जी सर.
ओके चलो ठीक है. So this implies beta Ji is equal to 0 for all 1 less or equal to I less or equal to N, 1 less or equal to J less or equal to M. Why so? Because this Wj, it is a basis of W. Cannot be linear combination 0 के बराबर है, that means every coefficient has to be equal to 0. So we are done. ठीक है. So thus B is linearly independent. Now since cardinality of B is equal to Mn, thus dimension of LVW is equal to Mn. ठीक है?